Hey everyone, and welcome. Today we're talking about a truly revolutionary material that's probably all around you, but you've never even noticed. We're going to get to know the plastic that thinks it's a metal, a material that's changing, well, pretty much everything. So let's just start with this one kind of wild question. I mean, we all know plastic stops electricity, right? It's an insulator. And metal conducts it. But what if you could smash those two ideas together? What if you could have the flexibility and lightweight of plastic, but with the electrical powers of a metal? Well, that's exactly what we're going to break down. First, we'll meet this wonder plastic. Then we'll see how it's already in the tech you use every day. After that, we'll look at clean energy. And then, this is the cool part, we'll explore the bionic frontier where this stuff literally meets biology. And finally, we'll ask, what's next? All right, first things first, let's pull back the curtain on this material that sounds like it shouldn't even exist and figure out what exactly it is. So, a conducting polymer is pretty much what it says on the tin. Scientists have figured out how to fundamentally re-engineer the molecules of a normal plastic, a polymer, to let electrons just flow light through it. It's a game changer in material science. The best way to picture this is to think of an electron superhighway. In your average plastic, that highway is full of traffic jams and roadblocks. Electrons can't get through. But in a conducting polymer, it's like all the lights are green. It's just a wide open, fast lane for electricity to zoom through. And that one simple idea, well, it opens up a whole universe of possibilities. Okay, so let's bring this out of the lab and into your life, because this isn't science fiction. This is the science that's probably sitting in your pocket as we speak. No, really. If you've got a smartphone with a beautiful, vibrant screen, or one of those fancy new TVs, you are looking directly at conducting polymers in action. They are the secret sauce behind the amazing paper-thin displays we all love. And this slide just lays it all out perfectly. On the left, you've got the old way of doing things, LCD screens that needed a big, clunky backlight behind them to light up. But on the right, you have OLEDs. They're built with layers of these conducting polymers, and here's the magic trick. They make their own light. Every single pixel is its own tiny light bulb, so no backlight needed. That's why screens got so much thinner, lighter, and way more energy efficient, which is a big reason your phone battery lasts longer. Oh, and yeah, it also means they can be flexible. Okay, so from the tiny screen in your hand, let's zoom way out to the big picture. Because these materials aren't just making our gadgets cooler, they're actually helping us build a cleaner, greener world. And it all comes down to how versatile they are. Because they're so light and flexible, you can make solar panels that you can literally roll up. Think about that. A solar panel you can unroll like a yoga mat to power your campsite. This tech is also making batteries that hold more juice and last longer. And that same OLED tech from your TV, you can scale it up to create incredibly efficient lighting for our homes and cities. And when I say efficient, I mean it. Check out this number, 90%. That is the potential energy we could save by switching from old-school incandescent light bulbs to OLED lighting. That's not just a small change. That could put a massive dent in global energy consumption, not to mention your own electricity bill. All right, now for my favorite part, the part that feels like it's straight out of science fiction, except it isn't. This is where we talk about what happens when this technology meets the human body. For decades, this was the big problem. Our bodies are soft, flexible, organic things. Our electronics have always been rigid, metallic, and hard. Trying to get the two to work together is tough. The body just doesn't like it. But what if your electronics were also soft and flexible? What if they could speak the same physical language as our bodies? This is where a property called biocompatibility becomes an absolute game changer. And this is where these polymers really shine. Let's walk through how a biosensor works. It's actually incredibly elegant. You've got a receptor on the polymer that's designed to grab one specific thing, let's say a glucose molecule. As soon as that molecule locks in, it's like a tiny switch gets flipped. The electrical conductivity of the polymer changes in an instant, and that change is read as an electronic signal. It's a perfect, seamless bridge between biology and technology. And believe me, it doesn't stop there. We're talking about developing artificial muscles that contract with a tiny bit of electricity, creating scaffolds that can help damaged nerves regrow, and building smart medical implants that can monitor your health from inside you and deliver medicine right when you need it. It's incredible stuff. So let's bring this all home. We've seen how this wonder plastic is already at work, from the phone in your hand to the future of our own bodies. These are the superpowers that make it all happen. Any one of these properties is cool, but it's the combination of all of them that's so powerful. It's light, it's flexible, and it conducts electricity. But then you add in energy efficiency and that all-important biocompatibility, the fact that it can work safely with our bodies, and you've got a material that is truly going to shape our future. I think this quote just nails it. We are leaving the age of clunky, hard devices behind. We're entering a new era, one where our technology is going to feel a lot less like a machine and a lot more like a natural part of our world. And really, that just leaves us with one final, huge question. We are only just beginning to figure out all the things we can do with conducting polymers. So with a material this smart, this powerful, what do you think we should build with it next? Thanks for tuning in.